So real quickly, I'm sure you all know the rules for integrals, so we're not going to go through all the regular rules for integrals. Just a brief review of how to do U substitution, just to remind ourselves, especially on ones that might be a little more, bit more difficult. So if I gave you something like x cubed times the square root of x squared plus 1 dx, just to make sure we know how to integrate this, we're going to do a U sub where U equals x squared plus 1, giving us du is 2x dx. So we'll put in a 2 and we'll put in a 1/2 out in front, and that will allow us to rewrite this as 1/2 of the integral of 2x times x squared times the square root of x squared plus 1 dx. And that'll let us write it as 1/2 the integral of 2x dx just becomes du. X squared becomes u minus 1. And square root of x squared plus 1 becomes u to the 1/2. Put it all together, 1/2 the integral of u to the 3/2 minus u to the 1/2 du, and then you integrate this and turn it back into terms of x by replacing all the u's with x squared plus 1. Everybody good with that on U substitution? The basic idea of the U substitution, just make sure that you build your du into your integrand and cancel out any constants that you put in. And if you have stuff that's left over, sometimes you'll have stuff that's left over that you can build what they equal from your original U substitution. Everybody good there? Okay. So U substitution should be pretty straightforward. Next thing is if we're looking at a rational function. So if you're asked to integrate a rational function, the polynomial over a polynomial, the first thing that you want to look at is right off the bat, number one, is there an easy U sub? Right, so you might see something like 2x plus 1, that's an integral of 2x plus 1 over x squared plus x plus 3 or something like that. And if you think about this, the denominator is a good candidate for our u, because if we take du, that just becomes 2x plus 1 dx, and that's what our numerator is. So we want to turn this into du over u and get natural log absolute value of u, and then replace it with the x squared plus x plus 3. All right, so first thing you want to do is look for an easy U substitution. Everybody good with that? Cool. All right. Always check for that. Second thing is this is still on rational function. So if you have something like the integral of, I don't know, let's go with 2x cubed plus x squared plus x plus 1 over x squared minus 1. Right, something like this. We would note that because the degree of the numerator is greater than the degree of the denominator, and there's no easy U substitution, the first thing that we're going to want to do is long division with this. And if the degree of the numerator is also equal to, so if this was x cubed minus 1, we'd still want to do the long division. Okay, so we're going to do x squared minus 1 into 2x cubed plus x squared plus x plus 1 to try and write this into an easier integral for us to deal with. So x squared goes into the 2x cubed 2x times. That gives us 2x cubed here, gives us 0x squared and minus 2x. And we subtract, we should end up with an x squared plus a 3x. And we can bring down the plus 1 if we want to. And then x squared goes into x squared once, so we'll have a 2x plus 1 put down our x squared and our minus 1, subtract, and get 3x plus 2. And so we'd end up with the integral of 2x plus 1, the thing we got with our long division, plus 3x plus 2 over x squared minus 1 dx. And so always divide through the long division first if there's not an easy U substitution. Everybody good there? Obviously, then you finish doing this integral, right? You get x squared plus x plus the integral of 3x plus 2 over x squared minus 1. And so what do we want to do to integrate 3x plus 2 over x squared minus 1? We should factor out that denominator and use the other technique that we have for rational functions, which is partial fraction decomposition. So I'm just going to go to the next page here. We'll finish this one up. We have x squared plus x plus the integral of 2x, what's 2x plus, no, 3x plus 2 over x plus 1 times x minus 1. And so we need to figure out how to decompose this into two different fractions. So we're going to start off. With a over x plus 1 plus b over x minus 1, because these are linear factors in the denominator. We just put a constant in the numerator. And that should be equal to 3x plus 2 over x plus 1 times x minus 1. And so then we will get the common denominator. So it's become a times x minus 1 plus b times x plus 1 equals 3x plus 2. All the denominators cancel out when we multiply to get that common denominator. And from there, we can set up a basic system of equations. We'll say that, there are a x's and b x's on this side. So a plus b needs to equal 3. And on this side, there are negative a and a positive b. And that needs to equal 2. We can then subtract one from the other. So if we subtract this, a minus negative a gives us 2a, b minus b cancels out, and 3 minus 2 gives us 1. So we end up with a as a half. If a is a half, then b must be 5 halves. Yeah, Kevin, you're welcome to just plug in x equals 1 and x equals negative 1 to solve for a and b. If you want to set up the system of equations, that is totally fine. They won't care if you do that. That's totally fine. And so then this now becomes x squared plus x plus our integral of 1/2 is our a value, right, over, or we'll just say 1/2 times 1 over x plus 1, and then plus 5 halves times 1 over x minus 1. So we got x squared plus x plus 1/2 natural log absolute value x plus 1 plus 5 halves natural log absolute value x minus 1 plus your constant. And that's the basic idea behind your rational function integrals. Everybody good with those? Yeah. Just to remind you for your partial fraction decomposition stuff, just to remind you how to set them all up. If you have something, and I'm just going to kind of make up some cases, we're not going to actually integrate these. But if we had something like x squared plus 1 over x plus 1 squared times x minus 1, the way that we would want to go about doing the partial fraction for this would be a over x plus 1 plus b over x plus 1 squared plus c over x minus 1. Right, we have a linear factor of x plus 1 that is repeated, so it gets two different instances of a constant, a over the first power of it and b over the second power. If it was a third power, we'd have also plus c over the third power of it. Since this one is also linear, it just gets a constant. If we had something like x squared plus 1 over x squared plus 2 times x, we'll just say times x squared plus 2 times x squared plus 3 squared. You'd have an a over the x because that's a linear piece, so it gets a constant in the numerator. You'd have a dx plus c over your x squared plus 2 quadratic piece gets a linear factor. Then you'd have a dx plus e over the other irreducible quadratic factor. And then f x plus g over x squared plus 3 squared. So since there's a repeated irreducible quadratic factor, we want to include 2 different instances of that. And anytime it's an irreducible quadratic, you put a linear piece up in the numerator. Everybody good with that? All good. Okay, perfect. Good. Cool. I think I have these all written down on the test reminder sheet that I gave you, but I just want to go through a couple of these real quick. This integral 1 over a squared plus x squared dx is one that pops up fairly often. This one you should know is 1 over a times the inverse tangent of x over a plus your constant. So, if you have a rational function that's in this form, that's just an inverse tangent one. So that one should be pretty easy. And then this one also pops up fairly often. Right, 1 over x squared minus a squared dx. Again, another rational function one. This one is a little different. It becomes 1 over 2a times the natural log of the absolute value of x minus a over x plus a plus your constant. So this one pops up pretty often too. So make sure you know both of those integrals. Everybody good there? Cool. All right. Not going to really talk about reduction formulas and all that, but I do want to just talk about the forms for tangent and secant. So if you end up with an integral that is, let's see, we'll just do tangent to the m of x, secant to the n of x dx. You want to break that down and just do a U substitution for this. So if your value for n is even, so if the power on the secant is even, you're going to want to let u equal tangent x. And if the power on m is odd, you're going to want to do a substitution where u is equal to secant x. And if both of those are true, then you can do the substitution using either one. And if neither of those is true, then you're going to have to do it some other way, right? And there's some integrals that you want to just know and have memorized, just in case you end up with one that is, where n is odd and where m is even and where n is odd. So you probably are going to either need the integral of tangent x for that, which you should know that you can do as sine over cosine as a u substitution, but also know that that is negative natural log absolute value cosine x. And oftentimes on the AP test, they'll write it as natural log of absolute value of secant x plus a constant. So it's just fine. That's just log rules throwing this negative 1 in as a power inside. So you should know that one. Definitely helpful if you ended up with like a cotangent cosecant integral also. That doesn't happen that often, but helpful to know that the integral of cotangent dx is just natural log absolute value sine x. And also really helpful so that you don't have to remember how to integrate it using adding stuff in and using a u substitution, that the integral of secant x is natural log absolute value secant x plus tangent x plus your constant. So that's a good one to know as well. The only other one that I would say, well, actually, there's probably 2 more I would say are good to know. you'd need to show the work on secant cubed x if you were doing it in the free response. You'd have to do it by parts, but it's not too hard to memorize this one. So if you just memorize it and it shows up in the multiple choice, that's going to make your life pretty easy. It's natural log absolute value secant x plus tangent x plus secant x tangent x all over 2 plus your constant. So that's a good one to know. And I always tell people that just so you don't have to worry about doing it by parts, it's good to know that the integral of natural log of x, it's supposed to be an x, not an s. I don't know why I wrote an s. Natural log of x is just x ln x minus x plus your constant. So those are the integrals that if I were you, I would just sort of have memorized in general. Yeah, so memorize those. Those will be good ones to know. You shouldn't need the reduction formulas on the AP test, so that shouldn't be an issue. Let's see what else. Oh, we need to talk about trig sub integrals, right? We haven't talked about trig sub integrals. So if you need to do a trig sub, well, if you see something that is in the form square root of a squared minus x squared, or square root of a squared plus x squared, or square root of x squared minus a squared, these are all good candidates for trig subs, unless there's a simple u substitution. So if I gave you this integral, you could do a trig substitution. You could go in and do the trig substitution with a squared minus x squared, which is a sine theta, do a 2 sine theta substitution here. But there's no reason to do that because you can let u equal 4 minus x squared, and then du is negative 2x. You'll just throw the negatives in and integrate that really easily using a u substitution. But if I gave you something like, 2x squared over root 4 minus x squared, then you're going to want to know that the substitution for a squared minus x squared, you're going to want to let x equal a sine theta. Right? Or if we have a squared plus x squared, we're going to want to let x equal a plus, or not a plus, a times tangent theta. And if we have x squared minus a squared, we're going to want to let x equal a secant theta. And those should turn these into a fairly simple integral to complete. Sometimes these integrals end up giving you secant cubed or secant that you need to integrate within them. So that's why it's helpful to just know those integrals. So let's just see if we can do 2x squared over root 4 minus x squared real quick. So we're going to integrate 2x squared over root 4 minus x squared. Recognizing that this is a u substitution, we're going to let x equal 2 sine theta. So first thing to remember when you're doing your trig sub integrals is that you need to figure out what dx is, and you need to replace the dx with whatever the derivative of x is. So in this case, 2 cosine theta d theta. So we're going to rewrite this as 2 times, and then we have x squared, so that's going to be 4 sine squared theta. And then we're going to have a 2 cosine theta d theta, which is our dx. And then in the denominator, we will have our square root of 4 minus 4 sine squared theta. Everybody good with that? Then we'll simplify. So we can pull the 4 out of here. When we pull the 4 out, don't forget that it's a square root of 4. So that's a 2 that comes out of there, which will cancel with this 2. We've got a 4 times a 2 still, which is going to give us an 8. So we'll have 8. And we'll have the integral of sine squared theta cosine theta d theta over, and then here this becomes just a 1 minus sine squared inside there, which is cosine squared, which we square root to get cosine. The cosines cancel. And we have 8 times the integral of sine squared theta d theta. And really important that that we know the power reducing formulas for these. And if we don't know the power reducing formulas, we're going to struggle on some of these like sine squared type integrals to integrate. So we should know that sine squared is equal to 1/2. So I'm going to cancel the 8 with the 1/2 and make it a 4. And then the integral, so the rest of that should be 1 minus cosine 2 theta d theta. And then we should be able to integrate that pretty easily. 4 times theta. And then minus, and then this is just the u sub, right? Theta minus 1/2 sine 2 theta. plus our constant. And we'll recognize that that is not the final answer we want. I'm going to write it out here as 4 theta minus 2 sine 2 theta. 4 theta minus 2 sine 2 theta, just for a second here. What we need to do with this, don't forget my plus C, is we need to go back and figure out what theta is and what sine of 2 theta is. So we'll want to make sure that we can draw our right triangles. This is our theta. We originally started off with the substitution that x was 2 sine theta, right? Or that the sine of theta was x over 2. So the sine of theta ought to be opposite over hypotenuse. You can use the Pythagorean theorem to find the third leg, or third side, the other leg. And it'll always end up being this original term that you had, this root 4 minus x squared is what this will always come out to be. So, if you started with a roots, 9 plus x squared, this, whatever your third side, which would happen to be the hypotenuse, if you're doing a tangent substitution, would be that same radical expression you started with. And from there, you should be able to tell, we already know what what theta is, because we just wrote this. So theta is the inverse sine of x over 2. So we should be able to say that we have 4 inverse sine x over 2. And then sine of 2 theta, well, we're going to need to know that that's the same as 2 sine theta cosine theta. So this will become minus 4 sine theta cosine theta plus our constant. So we've got 4 inverse sine x over 2 minus 4 times the sine of theta, which we know is x over 2. And then the cosine of theta, which should be root 4 minus x squared over 2 plus our constant. We can simplify. The 4 over the 4 goes away. And we have 4 inverse sine x over 2 minus x root 4 minus x squared plus our constant. Everybody good with that? We all remember doing these trig sub integrals? Cool. All right. I think that's everything with integrals. No, that's not everything with integrals. We didn't talk about integration by parts, which was a big piece of one of the things that we learned this year. So what we want to be able to do is take an integral of u dv, and we should know that that, according to the integration by parts formula, that is just derived from the product rule for derivatives. The integral of u dv is uv minus the integral of v du. And so whatever function that you have that you're trying to integrate over here, you need to break it up into 2 different pieces. One that's u, that you'll be able to take the derivative of, and one that's dv, which will include the dx term that you have inside the integral. And the dv needs to be a function that you can integrate. So traditionally, we will choose dv to be the most complicated, but still fairly easy to integrate function. And so as long as we can still integrate it, it's okay. We want dv to be the most complicated thing that we can still integrate. So the integral of u dv equals uv minus the integral of v du. If we had something like the integral of x sine x dx, we'd look at this and say, well, there's 2 different functions in here. There's x and there's sine x. The one that is easier, one that is easy to integrate but more complicated is the sine x function. So we would let u equal x. We would let dv be our sine x dx. And du would just be dx. And v would be the integral of sine, which would be negative cosine x. And so then we would just go straight through and fill in this formula. So the integral of u dv should be u times v, so negative x cosine x, minus the integral of v, which is negative cosine x du, so dx. And we can put the minus and the minus there together to just make that a plus the integral of cosine. So we have negative x cosine x plus sine x plus our constant. Everybody good there? Basic idea of integration by parts. We'll do a couple more to look at the, to look at tabular integration and sometimes what happens when we end up with the same integral that we started with within our integration by parts formula. But the basics of integration by parts, everybody good there? Cool. All right. So let's start with something like the integral of x cubed sine 2x dx. So we'd immediately recognize this as one that we would want to use integration by parts for. But we would note that if we try to use integration by parts, we're going to end up having to use it over and over and over again, like 3 different times to get to the final answer. We can get around that if one of our functions, the derivatives, eventually equal 0. Right? And so if I take the derivatives of x cubed, the derivatives of that will eventually be 0. And then we should be able to integrate sine of 2x as many times as we need to match up with the derivatives of x cubed. So the first derivative of x cubed is 3x squared, then 6x, then 6, then 0. We'll just list those all going down. And then we'll take the integrals of sine 2x. So the first one should be negative 1/2 cosine 2x. And then the integral of that ought to be negative 1/4 sine 2x. And then the integral of that ought to be 1/8 cosine 2x. And then the integral of that ought to be 1/16 sine 2x. And so we'll match these up. We'll take our first term here that we had that before we took a derivative and match it up with the first integral. And that term will always be just whatever sign you get from those two terms. So that would be, in this case, a negative 1/2 x cubed cosine 2x. Then we'll take the next two, and whatever the sign between those is, we will take the opposite of it. So this one, we just keep the sign. This one, we take the opposite of it. So the opposite of this is going to be a positive 1/4. So we're going to have a positive 3/4 x squared sine 2x. Then we'll take the next ones. Those will be positive. They just alternate positive, negative, positive, negative, positive, negative, positive, negative over and over until you're done. The 6/8 will just become a 3/4 again. So we'll have plus 3/4 x cosine 2x. And then our last one here becomes a minus. So we'll have a minus, and then 6/16 ought to just be 3/8. So minus 3/8 sine 2x plus our constant. And we remember that this is called tabular integration. It'll work when our derivatives eventually get down to being 0. Everybody good with that? Hopefully everyone's good. All right. So lastly, with integration by parts, we might have something that ends up being, let's say, the integral of, we'll just do an easy one here to see. We'll just do the integral of e to the x sine x dx. And we'll note that both those functions are fairly complicated. I mean, not like super complicated, but they're not just polynomial functions, nice, easy polynomial functions. And we'll note that neither of them, if you take the derivatives repeatedly, will ever become 0, right? E to the x will just keep being e to the x, and sine x will just be going back and forth between sine and negative cosine and negative sine and cosine and back to sine and so on. I think I said integrals there, but derivative, same thing, cosine, negative cosine, back to sine. So we'll do the integration by parts, and it's not really going to matter which one we choose here. Let's let u equal e to the x. And let's let dv equal sine x dx, giving us du is e to the x dx, and v is negative cosine x. So our formula says the integral of e to the x sine x dx ought to be negative e to the x cosine x, that's the uv, minus our integral of v du, so that's going to be minus negative cosine x times e to the x, so that's, we're going to make that a positive, e to the x cosine x dx. And so then we will just go down and, you know, since this is clearly an integral that requires integration by parts, we'll do the same thing. We'll let u equal e to the x. This time dv will be cosine x, and du will be e to the x dx, and v will be sine x. And so we'll have negative e to the x cosine x plus, and now it's our new u times v, so that's e to the x sine x, minus the integral of v du, which is the integral of e to the x sine x dx. And at this point, we note that the thing that we are trying to integrate within our problem is the same thing that we were starting with. So this whole thing, all of this that we've got, is equal to the integral of e to the x sine x dx. So we just take this one and add it to the other side, giving us e to the x sine x minus e to the x cosine x, if I just flip those around, is equal to 2 integrals of e to the x sine x dx. Well, I don't want 2 of them, I just want 1, so divide it by 2. We have the integral of e to the x sine x dx equals e to the x sine x minus e to the x cosine x all over 2. And don't forget your plus c. Conceptually, everybody okay with that? Hopefully. I hope so. And note that, you know, the coefficients worked out really nicely and easily, but suppose this had been like sine 3x and e to the 4x, the coefficients wouldn't have been great. We would have ended up with like some ugly fraction in front of here. You just cross multiply and be done with it. Everybody good there? All right. Cool. So I think that's, if I'm remembering, we talked about Riemann sums, we talked about all the integration stuff other than these rules. We talked about area, we talked about volume, we talked about arc length. That should be everything with integrals. Does that sound about right? Anybody think we're missing anything from limits, derivatives, or integrals from this time or last time? No surface area. Now that's just something I threw in because it's you know, interesting to look at some of those shapes and their surface areas and all that. No surface area. No surface area and no volume by shells. You don't actually have to use cylindrical shells for anything. You can if you wish, but you don't need to. So if something works out nicely with shells, go for it, but don't feel like you need to. And there will never be anything that requires you to use shells to find volume. All right. Oh, we didn't talk about improper integrals last time, did we? All right, so there's not a lot to say about improper integrals, other than make sure. Oh, we didn't talk about differential equations last time either, did we? I don't think we did. We'll do those too. So in terms of improper integrals, you know, we're talking about something like an integral from 1 to infinity of, you know, 1 over x dx or something like this, or an integral from negative infinity to 0 of 1 over x minus 1 dx, or, you know, something like this, where the limits of integration are negative or positive infinity. So these always need to be written out as a limit as a approaches infinity of an integral from 1 to a of 1 over x dx. Or in this case, a limit as b approaches negative infinity of the integral from b to 0 of 1 over x minus 1 dx. Everybody good with that? And then you just integrate as normal. Just make sure that you integrate, evaluate your integral in terms of a or b first, and then look at what the limit is. Okay? And oftentimes you might end up within here with an integral that looks, or with your final value for your integral that's something like the limit is, well, it doesn't really matter what the limit is, but you might end up with something like natural log of, absolute value of x minus 2 minus natural log absolute value x plus 2 or something like that. And if you were to think about this, you might, if you try to plug in infinity to these, so suppose we have a limit is, well, let's just say it's a minus 2 minus the natural log of a plus 2, something like that, as a goes towards infinity. This looks like it's infinity, and this looks like it's infinity, so a first inclination might be to just immediately say that this diverges. But remember that you can write this as the natural log of a minus 2 over a plus 2. And then you look at what's going on as a goes towards infinity. The argument of the natural log is going towards 1, right? So you could let u equal a minus 2 over a plus 2 if you even wanted to write it out and be more thorough. You then say as a approaches infinity, u is approaching 1, so this becomes the limit is u approaches 1 of the natural log of 1, right, which ends up being 0. And you'd have some other pieces over here with some numerical parts, and you'd end up with like an answer of natural log of 7 or something, depending on what your limits were. But just make sure that if you get this, that you remember that infinity minus infinity is indeterminate, and you need to find a way to combine those together, often using logarithms. Everybody good conceptually with that? Hopefully so. All right. And then, of course, improper integrals can also occur, if we have a vertical asymptote, right? And I ask you, suppose there's a vertical asymptote here at x equals 1, and I ask you, what's the integral from 0 to 1 of this function, right? That's also an improper integral since we're approaching a vertical asymptote. So we would just say what's the limit as a approaches 0, in this case from the left, of the integral from a to 1 of f of x dx. And if I was doing it from the other side, we'd be approaching 1. I said 0, but I meant that's not 0. Limit is a approaches 1 from the left. And I don't know what I was doing there. I wrote those backwards. Sorry, 0 to a as we approach 1 from the left, as a approaches 1 from the left. Good? Does that make sense? If you're looking for the area between 0 and the vertical asymptote of some function. We all basically remember those. All right, cool. Let's see, and just remember that if anywhere within your limit you get an integral that or a value that equals infinity, or that it shows that it diverges, then the whole thing will diverge. And like I said this earlier, but if you don't write it in the limit notation, they will give you 0 points in the free response for these, right? If you're just being hasty in the multiple choice and don't feel like writing out the limit and just leaving the infinity up there, I mean, that's bad math, but no one's going to know, and it's fine. But on the free response, if you don't put the limit notation in it, you will get none of the points. So please don't try to do it without the limits. That would be bad. All right. In terms of differential equations, things that we want to talk about real quickly. First off, we talked about two main types of differential equations. One is the exponential growth equation, differential equation, which is dy dt equals k times y, right? And this just means that the growth of y is proportional to the amount of y, right? And this differential equation can be solved by separating the variables, right? Dividing by the y, multiplying by the dt, integrating both sides. But it always, 100% of the time, comes out to be y equals y naught e to the kt. And if the value of k is positive, it's exponential growth. And if the value of k is negative, it's exponential decay. So you don't need to, in the multiple choice, if they give you this, and then they ask you about, how much of something there is after a certain number of years, you can jump straight to this equation. If you started with the differential equation, d by dt equals ky. And k is just a constant. It varies from problem to problem depending on the rate of growth or the rate of decay. Let's see what else to say about that. Not much else to say about that. Exponential growth stuff should be pretty straightforward. The other main type of differential equations that we talked about was our logistic growth. And your logistic growth equations come from, we usually write them as dp dt because we're talking about population, k times p times m minus p. And we should know that this, can also be done by separating the variables, right? You can divide by the p and the m minus p, and then you can do partial fractions with that and multiply by the dt and integrate the k dt and solve. But this should always come out to be, well, it will always come out to be, the population is equal to m over 1 plus m minus p naught over p naught times e to the negative mkt, 100% of the time. So that is done by separating the variables and then using partial fraction decomposition to integrate. We want to remember a few things about our logistic growth equations. Number one, that m we call the carrying capacity. And so m is our carrying capacity. That is the maximum value that our population could ever reach. Okay? And we also want to remember that they ask this sometimes, that the population increases most quickly at 1/2 of your carrying capacity. Okay? And they also often like to ask about limits regarding logistic growth equations. So if we talk about the limit as t approaches infinity of the actual population of the final of p of t, that's always equal to your carrying capacity, right? As time goes towards infinity, your population is going towards its maximum value, to its carrying capacity. And sometimes they will also ask what's the limit as t approaches infinity of the differential equation itself of dp dt. And the answer to that should always be 0, because we should know that the logistic growth equation looks like this. And so as we go towards infinity and are approaching this maximum value of our population, we're narrowing out so much that effectively we're becoming like a horizontal line as we approach that horizontal asymptote of our population. And so the limit as t goes towards infinity of the rate of change of the population is 0, because effectively it's going towards 0. Let's see. And if they ask you when does the population reach its carrying capacity, you always, so suppose if the carrying capacity, let's say that was 500. If they ask you when does it reach, when does it hit 500, you will just do 499.5 equals your, equals your dp, not dp dt, equals your p of t equation that you figured out. So you'll just do the half of a unit increment below that so that it rounds up to it. And then you'll solve for t within your p of t equation. They may ask when does it, when is it increasing more, at what time is it increasing most rapidly? Well, then you'll, take half of your carrying capacity, put 250 equals your P of t and solve for t. And then let's see, other thing I wanted to say about this. Population increases most quickly at 1/2 m, and this is a point of inflection at 1/2 m, right? At 1/2 of the carrying capacity, the graph hits a point of inflection, goes from being concave up to being concave down. Everybody good there? All right. We have a couple of different ways to approximate the value of a function when we're using differential equations. The first is generally used to approximate the solution curve, so slope fields, right? A couple of things to remember about slope fields. Number one, they don't have to be perfect. They just have to look pretty good, right? It has to, if your slope of 1/2 looks more like 1/3, you're going to be fine. If your slope of 2 looks more like a slope of 2.3, life's going to go on. You're going to be fine. But a couple things to remember about slope fields. If they ask you to sketch the solution curve, and if they ask you to sketch the solution curve, number one, don't put arrows at the end. Because their slope field that so they're going to give you a slope field. If they ask you to sketch the solution curve, usually they give you the slope field. Don't put arrows at the end of your curves, because the slope field that they give you is only what is defined in the graph that they give you. It does not necessarily continue in the same way afterwards. So just end it at the bounds of the region. Don't extend beyond, but make sure you extend it all the way to the end of the graph that they give you. Okay. If you leave it short, they will not give you the points. If you leave it, even if it's just a little bit short, they will not give you the points. Make sure you get it all the way to the end. And you don't need to put like a point to end it there. You can just end it at the end of the axis that they give you. And the last thing to remember, if you're sketching the solution curve on a slope field, is always make sure your curve, my handwriting, always make sure your curve is a function. Because remember, we have the interval of validity for our solution curves for our solutions to our differential equations, and that we need to make sure that we have a function, and make sure that it's on that interval that they've given you, and make sure that it doesn't, do anything. You don't want to sketch this as the solution curve, right? Even if that's what it looks like, you don't want to do that. You want to sketch only one piece of it, depending on where your point is. Everybody good with that? Cool. All right. In terms of sketching your own slope field, which is a possibility, if you have to sketch your own slope field, like I said, it doesn't have to be, the slopes don't have to be perfect. They just need to be pretty close. But usually, when sketching, if you're making your own slope field, there are usually 2 points associated with it. The first point is the zero slopes. The second point is all the other slopes. So make a point to note when your slope field should have slopes of 0 at the indicated points that they give you, and then make sure that you get those ones correct, because that's half of the points for your slope field when you sketch it. Okay. Everybody good there? The other thing that they might have you do to approximate the solution to a differential equation is Euler's method. I remember talking about Euler's method, hopefully. And Euler's method just means you're going to take the initial point that they give you, and then you're going to figure out what the value of dy dx is at that point, because they're going to give you dy dx. You're going to need to figure out what your delta x step is, how much is x changing. So if they say you need to go from 1 to 2 in 4 steps, well, then delta x ought to be a quarter. If they say you need to go from 1 to a half in 5 steps, then your delta x needs to be negative 0.1, right? If you're going to go from 1 to a half. All right, so you're going to take that step, that delta x step, and multiply it by dy dx to figure out the change in y. And then you will have a new point, which will be x plus your delta x and y plus your delta y. And then you'll just repeat again with that next point. Right? So effectively, I'm not going to go through the whole thing, but if I said dy dx is x plus y, and we were starting at the point 1, 1, and our delta x was going to be 1/2, let's say, we would go through and we'd say we'd start at 1, 1. I'll draw it on the chart. We'd start at 1, 1. Our dy dx would be 2. Our delta x, like we just said, is going to be 1/2 times our dy dx, which was 2, giving us a delta y value of 1, giving us a new point of 1.5 for x, right? Our x plus our delta x. And then our delta y was 1, so 1 plus 1 is 2. And so that would become our next point over here. And we do the same thing. The next slope would be 3.5. So we do 0.5 times 3.5, and so on, until you got up to whatever value they asked you to get to. Everybody feel okay about that with Euler's method there? Wonderful. Okay. Now I think that's everything other than series. Does that sound right to everybody? I'm going to just sit here for a second and see if I think of something else, but I'm pretty sure we got everything. Did I talk about the mean value theorem for integrals last time? Just in case I didn't, we'll just mention it right now. We're at the average value. That's the average value of a continuous function. So this is just an easy one. You should know that it's 1 over b minus a times the integral from a to b of f of x. Right, so if I asked you for the average value of natural log of x on the interval from 1 to e, let's say, we do 1 over e minus 1 times the integral from 1 to e of natural log of x. So we have 1 over e minus 1 times x ln x minus x, because you memorized that one, because I told you should, which gave you what here? It gives us 1 over e minus 1, and then it gives us e times the natural log of e, which is 1. So e times 1 is e minus 0 minus 1, and we end up with 1 over e minus 1 is the average value of ln x on the interval from 1 to e. Good or no? Hopefully good. All right, on to series. So with series, the first types of series that we looked at were geometric series. Okay. And we'll note that a geometric series just has a common ratio r between terms. And any geometric series where the absolute value of r is less than 1, the geometric series will converge. Any time where r, the absolute value of r, is greater than or equal to 1, it will diverge, okay, no matter what. So easy. If you can find a common ratio between the terms and it's less than 1, or its absolute value is less than 1, it converges. If it's not, it's going to diverge. And if it does converge, it converges to the first term, a over 1 minus r, right? A is the first term. And so we took this idea and we applied it to what we called power series, where we looked at a series with a common ratio of x. And so as we did that, we first came up with a series for 1 over 1 minus x. And we said that 1 over 1 minus x is always equal to the sum from n equals 0 to infinity of just x to the n, right? That's a over 1 minus our common ratio, x, and it's x to the n, so that each successive term is being multiplied by x. And we manipulated this series in multiple different ways to come up with the series for lots of other functions. So, for example, 1 over 1 minus x squared should just be the sum from n equals 0 to infinity of x squared to the n, or x to the 2n. Right? Or if we wanted it to be 1 over 1 plus x, we would just make this the sum from n equals 0 to infinity of negative x, replacing the x here with an opposite of x, to the n, which we would normally, if we have a negative in there, write that out as negative 1 to the n, x to the n. And the negative 1 to the n is going to indicate to us that the series alternates. And anytime you have a negative 1 to an n, series will alternate. Everybody good with that? Okay. We then took derivatives as well as integrals of our power series. I think I mentioned at the beginning, we call these power series. Anyway, we took derivatives and integrals of them. Oh, all right. Run fast, Delphine, at your practice. I guess don't run too fast at your practice. When's the next track meet?
I think it's next Thursday.
Next
At
Thursday.
Cathedral.
Are you running 32? Are you running 16? What are you running?
I don't know yet.
All right. Keep me updated. Let me know for sure when it is and what you're running.
Okay, will do. Thank you.
Yep. Have a good practice. All right. So we're talking power series, and then there were 3. Okay. So we're talking power series. Right, power series. Yeah, I was going to say, we took the derivatives of these, we took the integrals of these as well to form new power series. And you can do that with any power series that you wanted to. So if we wanted to find a series to represent the derivative of 1 over 1 minus x, we would just take the derivative of x to the n. So, right, taking the derivative of this gives us nx to the n minus 1. And we would note that we'd go not from n equals 0 anymore, but from n equals 1 to infinity. We'd have to go up that one power there if we started at 0, and that gave us a negative exponent. And so this should be the series for the derivative of 1 over 1 minus x. And we do the same thing with integrals. When you take the derivative, your interval of convergence is always the same. When you take the interval of convergence, the base interval of convergence is always the same, but you also have to check the endpoints of it to make sure that the new one doesn't also converge at the endpoints. And so we'll get to some of the ideas on how we did that when we talk about all the different tests that we worked through when we were learning about series. Just remember that when you are integrating, let's suppose we were going to integrate the one for, well, we'll just do it for, I don't know what's a good one we should do it here for. Let's just integrate the series for 1 over 1 minus x. Oh, and now there are 2 of you. All right. So if we wanted to integrate the series for 1 over 1 minus x, that'd be the integral of our x to the n series. And we have two different ways we can go about doing this. One option is we can choose a lower limit that we know is going to work out nicely for us, but the other is to just do an indefinite integral. So if we're going to integrate from n equals 0 to infinity of x to the n, if we want to, we can do it with the definite integral and figure out what the constant itself is. So that would give us x to the n plus 1 over n plus 1 with our sum from n equals 0 to infinity, right, as our thing here, plus some constant. And we would note that, let's say, if we wanted to look at this series when x is 0, what's the integral of 1 over 1 minus x? That should be, this integral itself is negative natural log absolute value 1 minus x, right? And so if we plug in x equals 0, this series should be the sum from 0 to infinity of a bunch of zeros, 0 plus 0 plus 0 plus 0, so we end up with 0 plus our constant. And on this side, if x is 0, we end up with negative natural log of 1, which is 0. So that tells us that our constant is 0, and we just have this series. Alternatively, we could have said, well, let's make our lower limit 0. If we wanted to make our lower limit 0, we would choose 0 because we knew that if we plugged in 0 to this original thing, it gives us 0. And so we would know that the constant was going to become 0. But if there's not a good value for us to plug into the actual integral of the function, then you got to do it as an indefinite integral and find the constant. If you find the constant is like, plus natural log of 7 or something like that, that's fine. It just goes outside the summation. So natural log of 7 plus your series, and then that's it. The two of you left here good with that? All right. So let's see, that's the basics of power series. I gave you a bunch of different series that you need to know, a bunch of different power series. So I'm not going to write them all out right here, right now, but you need to know the one for e to the x, you need to know the one for sine of x, you need to know the one for cosine of x. Definitely the ones we just talked about, 1 over 1 minus x and 1 over 1 plus x. You should know those ones. I think I put on there natural log of 1 plus x. I think I put on inverse tangent of x. And just remember that any of these series can be manipulated. If I wanted to make it sine of x squared, I just replace all of the x's in the sine x series with x squareds. If I want to make it natural log of 1 plus 1/3 x, I just replace all the x's with 1/3 x. Right? And as you're going through, suppose your suppose your original interval of convergence for something was, let's say for e to the x, the original interval of convergence is negative infinity to infinity. If you replace the x with a 2x, well, 2x is then between negative infinity and infinity, which still tells you that x is as well. But if you have something like, 1 over 1 plus x, right? If your series for 1 over 1 plus x, which we know, right, is the sum from n equals 0 to infinity of negative 1 to the n times x to the n. This one converges, right, for absolute value of x less than 1. Well, if we were to replace the x, this is 1 over 1 plus x. If we wanted to make this 1 over 1 plus 2x, well, then this would become the sum from n equals 0 to infinity of negative 1 to the n, 2x to the n. And so now we would note that the absolute value of 2x is less than 1. And that's when this converges. So that'd be for the absolute value of x is less than a half. So make sure that if you change the value of x in your power series to some other function, that you resolve and find a new interval of convergence for it. Okay. Everybody good with that? All two of you. Cool. All right. Let's see. We talked about p-series and harmonic series. So like the harmonic series, sum from n equals 0 to infinity of 1 over n. This is, if they just say the harmonic series, this is the harmonic series, and it diverges. But the alternating harmonic series is sum from n equals 0 to infinity of -1 to the n over n. This is the alternating harmonic series, and this one converges. And we would note that it converges conditionally because the absolute value of it, which is this 1 over n series, diverges. And then as far as the p-series test, this is a special case. The harmonic series is just a special case of the p-series. The p-series test tells us that the sum from n equals 1 to infinity of 1 over n to the p will converge if p is greater than 1, but that it will diverge if p is less than or equal to 1. So the case where it's equal to 1 is your harmonic series. The case where it's less than is if you got like a root down there or something, or a negative exponent, which would just bring it to the top and clearly show that it gets bigger. But if p is greater than 1, like n squared or n to the 1.7 or something, it's going to converge. Everybody good there? Okay. Now, sometimes we would take a series, and in fact, we'd call them a Taylor series, right? A Taylor series, and we would generate a Taylor polynomial from them. And so the way we would generate the Taylor series or the Taylor polynomial for any function, right? For any function f of x, the Taylor series at 0, which we also call the Maclaurin series, right? If it's a series at 0, Taylor series at 0 is just called Maclaurin series, is always f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus f triple prime of 0 times x cubed over 3 factorial, and so on for as many terms as we want if it's a polynomial that we're going to truncate, or to infinity if it's a series. And this should allow us to write out a series for basically any function that we want that we can take its derivatives of. Note that we could replace the x equals 0, let's say it was x equals 1, then we would make these x minus 1s instead of x's, right? And this is, if we do this, it is not a Maclaurin series, right? A Maclaurin series is just when it's centered at 0. And so we often then take the Taylor polynomial and truncate it somewhere and say, all right, let's use the second degree Taylor polynomial to approximate the value of whatever function this one represented in. And so if we do that, when we talk about a second degree Taylor polynomial, we're talking about the degree, the power of it. Right, so if I say the second degree Taylor polynomial, that does not mean 2 terms. That means enough terms up until we get to an x squared. If I say the 5th degree Taylor polynomial, you put in all the terms until you have x to the 5th, right? You do not need to, it's not 5 terms, it's terms up to x to the 5th, which sometimes pops up when you're looking at like a series for sine x or cosine x. If they say, if they're talking about the series, let's say for cosine x, and let's say they say the second degree Taylor polynomial, well, that's just going to require 2 terms, right? Because the first term of cosine x is a constant. The second term, when it equals 1, is already squared. Not n equals 1, but it's up to n equals 2, and it's not 2 terms, it's the second degree Taylor polynomial. Makes sense to the couple of you still here? We've now added in somebody else that's from AB. Well, welcome, Sid. We're talking about series. It's very interesting. Everybody good there? Cool. All right. And then in terms of truncation error, which is something we need to talk about. So truncation error. Gotcha. So in terms of truncation error, if we have a geometric series, the truncation error is just the next term times the original series, right? And so we'll know that since we're talking about a geometric series, if these terms are going to be getting smaller if this thing converges, right? Because that's just, because r is going to be less than 1, they have to be getting smaller. That means that the full value of the series times that next term is some fractional value. So this is going to be less than the actual value of the series. So our truncation error for a geometric series is just the next term times the series. If you have an alternating series, and remember the criteria for an alternating series, is just that it alternates, right? So if we have an alternating series, the truncation error should just be the next term, right? That's it. And then the error for anything else that's not geometric and not alternating can be done using the Lagrange error bound. And your Lagrange error bound says that your error, which they will often write it out as the absolute value of the whatever degree Taylor polynomial, at whatever value we're looking at, minus the actual value of the function, that's their error, should always be less than or equal to the n+1 derivative at c times x minus a, if we're not centered, to the n+1 over n+1 factorial. Right? And this is our Lagrange error bound. And we will note that c is the value that makes the derivative largest on the interval from x to a. And so that will be the upper bound on the error for the truncation of any Taylor polynomial, or the truncation of a Taylor series into a Taylor polynomial. And so usually they will either give you some function that it's easy for you to figure out what the largest possible value of that derivative is, or they will tell you the largest possible value of that derivative on the interval that they give you in the free response question. Any questions on any of the error bound stuff? What do you mean, Kevin? What if you're able to find the actual value of the series? Like, oh, can you put the actual error? They will usually ask you for the upper bound on it using a specific test. So they're going to, not specific test, but using a specific bound. So they're going to want the bound rather than the actual error. I've never seen them ask for the actual error. So yeah, don't put the actual error if you can find that, even if you can find the value of the series. Just give them the upper bound on the error based on whichever test is the appropriate one for the series that you have. Unless they specifically say, how much is this off by? Right? If they specifically say that, which I've never seen them do, but it's, it's 100% possible they could give you a geometric series or something, or any series that you could find the value of, or and just, if you can find the value of it based on methods from this class, then it should be easy enough to put the actual error if you want, but only if they ask for it. Okay. Let's see, some of our rules, I'm not going to go through all of the rules for series probably because most of them don't appear that often, but the ones that you definitely want to be aware of are the direct comparison, right? Direct comparison test for series just tells us that if our series, and remember, very important. Remember your initial condition. So just like almost all of these, the direct comparison test says we have to have all positive, or well, really all non-negative terms. I keep saying positive, but it's okay if the terms are 0. So all non-negative terms, right? And if if we have a sub n is ours, or we'll just say if a sub n converges and b sub n term by term is less than a sub n, it also converges, right? And vice versa. If we have all positive terms and we have, all non-negative terms, and we have a divergent series that we know of, and the series we're looking at term by term is larger than our series that we know is divergent, then ours must also diverge. So that's the direct comparison test. Usually, it's used on things like, 2n minus 1 over 3n squared or something like that, where you could say, well, this breaks down to the idea of 1 over n, or better, 2 over 3n, and you would directly compare it to 2/3 n, which we know diverges because it's just 2/3 of a divergent series, the harmonic series. So you would just directly to it, and so on. Oh, we got more people from AB showing up to the. We have just as many AB people now in the BC review session. Weird. Okay, so that's the direct comparison test. The other good ones that you should know are the limit comparison test. You want to be brushed up on that because every once in a while on the AB test, that works out nicely. So the limit comparison test just says that if we have two non-negative series and the limit as n approaches infinity of a sub n over b sub n is some value c, where c is less than infinity and greater than 0, they both converge or they both diverge, one or the other. And so you just need to know one or the other of them, and whether it converges or diverges, and then you'll know that the other one is. If this limit comes out to be equal to 0 and b converges, then a converges, right? And that should make sense because if that limit comes out to be 0 and b is in the denominator, that means that b is getting larger more quickly than a if the limit goes towards 0. And so if b converges, then a must also converge to some other value that is going to be less than the b value for b. And if it comes out to be infinity and b diverges, same thing, then a diverges. And that's the same basic reasoning there, that because if b is divergent and this thing is still going towards infinity, that means the top must be getting bigger even more quickly than the bottom is for it to go towards infinity, so a must also be divergent. Everybody good there with the limit comparison test? All right. The integral test is another important one for us to know. So our integral test for series has a few more initial conditions that we need to have met. So for our integral test, our series has to be positive and it has to be decreasing. The series must be positive and decreasing. And then the function that we're going to take the integral of has to be positive, has to be decreasing, and it also has to be continuous for this to work. Okay. And so basically all the integral test says, and it's the way we proved the p-series test, the integral test says that all we have to do is integrate the function. And if we integrate the function from wherever we're looking at, and it converges, or diverges, okay, then so does the series. And the important thing to remember about that is that if the integral converges, you get some value for it. It does not mean that the series converges to that same value. It just means that the series also converges, right? But not necessarily to the same value. It could be the same value, but chances are it's not. So that's the integral test. Just make sure that if you're going to use the integral test, that the series and the function are both positive and decreasing, because this is the only test that we've used that requires that extra little piece where it's decreasing as well, and then the function would have to be continuous. And then we have both the nth root test and the ratio test. And the ratio test is like, that's like our big gun. Like that's the one that we really need to know and that is asked most often of us. The nth root test is just sometimes helpful. It says we can find the limit as n approaches infinity of some series, a sub n, to the 1 over n. And when it comes out to be whatever the limit is, if L is less than 1, it converges. If L is greater than 1, it diverges. And if L equals 1, it's inconclusive. Well, the ratio test gives us the same exact results. The ratio test, though, requires us to look at the limit as n approaches infinity of the n plus first term over the nth term of our series. And then all of this same stuff applies. And this is the one that gets used most often on the free response questions on series. I guess those of you that are, Megan, are you in this quarter or you're in last quarter, right? So we had a quiz today on this, but the ratio test was important for the ones on today's quiz. And so you just go in and you take a look at your series and you do your ratio test. And once you've done your ratio test, you should get the base interval of convergence. Right? So after your ratio test, let's suppose we got something like the L was equal to x over 3. Right, well, so since this is not less than 1 or greater than 1 for all values of x, we figure out when is it less than 1. And so that'd be when the absolute value of x is less than 3, right? We should multiply by the 3. And so that would tell us that the interval here would be x is less than 3, x is greater than -3. And then we would need to check the endpoints. And we would check our endpoints by going back and plugging in -3 and 3, both into our original series for x, and breaking that down into just a series with just n's in it. And then we'd use whatever test we felt like worked best. Is usually like an alternating series test or a p-series test or something like that, so that we can check whether the endpoints converge or not. And remember, when you check the endpoints, you have to check not just the endpoint as it is, but also the absolute value of each of those endpoints. When you plug them in and then boil that series down, simplify that series down, take the absolute value also, because they potentially will ask you, when does something converge absolutely and converge conditionally? And so you want to be able to give them all those things. And remember that your radius of convergence, if you get down to something like the absolute value of x minus potentially minus an a, is less than r. This is your radius of convergence. So if they ask you for your radius of convergence, you've just got to use, let's say, the ratio test, or the nth root test, or whatever test you feel like it's going to work. Get it in this form and figure out what r is. If there's a 2 here, that's not okay. You got to divide by the 2. Right? It has to just be an x with a coefficient of 1 plus or minus any constant for your radius of convergence. Good or no? Kevin, you're good too?
Yeah, just assume that I'm good on everything.
I usually do. All right. Cool. That, I believe, is everything that we talked about in the class this year. It took us about 3.5 hours, it looks like, total to get through it, to get through an entire 2 semesters worth of calculus. Not bad. Do either of you have any specific questions about anything that you'd like me to go a little more in depth on, or are you feeling pretty okay after all of that? Okay, so I'll leave it as, since there's really only 2 of you that are here from BC right now, I'm happy to stick around for the next 30 minutes and like start going over some of the questions from that extra test. Would you guys like to do that? Yeah, all right, sounds good to me. Okay, so I'm just going to pull up some of the, we're going to look mostly at the multiple choice ones. So I had it up a second ago. There we go. Now I got it. Okay. So the first one I wanted to look at, and you'll find that most of these are pretty straightforward. Like I'm just going to throw a couple up here and so you guys have an idea, because I know Megan, you were in AV last year, but you didn't really take the normal AP test. So like there's questions in here, like question 1 on this test that I'm looking at is just, what's the derivative of this? Right. So I mean, I'm not going to go through and do it, but like you guys can take the derivative of that, right? You just use the product rule and take a derivative, and pretty straightforward. The next one is, you know, let's see, you know, something like this. The limit is x approaches -7 of x plus 7 over the absolute value of x plus 7. And this is a question, in fact, this is a question type that they really like to put on. They want you to know what this graph looks like, or recognize that you need to look at it from the left and from the right because of the absolute value. So this is actually a good one for us to, even though it's easy, it's a good one for us to really quickly talk about. If they say what's the limit as x approaches -7, and even you AV people that have crashed in here, it's a good one for you to talk about too. So if you try to plug in the -7, obviously you get 0 over 0. So what we have to do is we have to think about what's happening with absolute value. If we take the absolute value of something that's positive, so like if we're approaching this from the right-hand side, we're going to get a positive value here, right, in the denominator. So this will become x plus 7 over x plus 7. Right? But if I'm approaching this from the left-hand side, didn't have an absolute value there, then because if I plug in -7.0001 to -7 plus 7, I get a negative number. I have to take the opposite of that thing that's in the denominator. And so this limit comes out to be 1, and this limit comes out to be -1. So oftentimes they'll ask for it from the right. Sometimes they'll ask for it from the left. Sometimes they'll ask for the 2-side limit like they did on this one I'm looking at, and the answer would be it doesn't exist. Does that make sense to all of you? Cool. All right, let's take a look here at this one. Here's a series. We have pi over e minus pi over e squared plus pi over e cubed. A lot of terms out here unnecessarily, that's fine. And then they've given you the general term, -1 to the n plus 1 pi over e to the n. Right? So then they ask, what is the sum of this series? Or one of the options is that it diverges. So we would note that if we're looking at this, what is the common ratio between the terms here? You should see that each one is being successively multiplied by -1 over e. Right? And so this is really just a geometric series with a common ratio of -1 over e. And since the absolute value of 1 over e is less than 1, we should know that this thing should converge. It should converge to the first term over 1 minus -1 over e. So that gives us pi over e over 1 plus 1 over e. And you need to be able to simplify this down, you get yourself a common denominator here. And so when you flip that around, you're going to get pi e over e times e plus 1. And your e's will cancel, and you get pi over e plus 1. Right, so there's a nice, easy series multiple choice question. You guys good with that one? Cool. All right. I know I was talking the other day about how they sometimes like to put in ones like this. So let's say we've got something like this. They give you some function, and they say, what's the limit as x approaches some value of your function minus f of that value over x plus 1. And so we would note that this is the limit definition of the derivative, right? This is the limit as x approaches a of f of x minus f of a over x minus a, with x equal to -1. So this is just the derivative of this function, 3 times x squared plus 1 squared times 2x. Not sure how that little line got there, times 2x at x equals -1. And so that should give us 3 times 2 squared times -2, which ought to give us what, -24. Good or no? All right, cool. Let's see here. Let's find another good one here. Let's take a look at this. 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial. They sure do like to give a lot of terms. Plus x to the 8th over 4 factorial, and so on, where the series looks like -1 to the n, x to the 2n over n factorial. And they want us to figure out, what does this converge to? And these are the options that they give us. Cosine x squared plus sine x squared, 1 minus x sine x, cosine x, and e to the -x squared. So how would you go about this one? Hopefully you look and note that one, the -1 at the end is just going to make this thing the alternating thing, and it just means that we are going to throw this -1 in with the x when I can work with this x to the 2n. So x to the 2n is the same as x squared to the n, right? Those are the same thing. So really, we should have -x squared to the n over n factorial. And so hopefully we recognize that this is some function to the n over n factorial, which is the series for e to the x, or e to the u. So this should be e to the u, e to the -x squared. Does that make sense? Excellent. Okay, let's look here. Oh, hold on one second. You may have a second. I got a text from a parent on my kid's baseball team. Give me half a second here. Okay, sorry about that. Okay. kid wanted a ride. My kid's parent was asking if I'd give him a ride to practice, but I'm not taking my own kid to practice. My parents are taking him because I have to go to school and run the clock for basketball games in a minute. So I don't know. I don't know how that kid's going to get to practice. Let's see here. Let's see here. Oh, here's a good one. They like to do these ones. And this is not specifically BC only. This is an integral from 0 to x. No, I can't read. That's not x squared. 0 to x cubed cosine of t squared dt. And then they want us to know what is f prime of root pi. So how do we go about this? Since this is f of x is this integral, the derivative of the integral, right, f prime of x ought to be just this function cosine of t squared evaluated at x. So that'd be x to the 6th. And then times the derivative of the x cubed. So that's 3x squared cosine x to the 6th. And so if we're going to evaluate that at root pi, this is the important piece of it. And evaluating is pretty straightforward. But this is the important piece of it. Can you do the fundamental theorem of calculus piece? So don't forget that you have to evaluate this at x cubed, so x to the 6th, and then multiply by the derivative of the x cubed. So then if you evaluate that at root pi, that should be 3 times root pi squared times the cosine of pi cubed. And root pi squared is obviously pi, so we get 3 pi cosine pi cubed. Good or no? Yes. Oh. Okay. Cool. Yeah. I just saw your thing there. The sum of 1 over n squared is pi squared over 6. That's just saw you. I don't know why we're asking that, but that's fine. Pi squared over 6. Good times. Okay. Here's fun one. I guess really that fun. R equals 2 theta squared. We want to know the slope of the tangent line to this when theta equals pi. So we got to remember how we go about our slopes of our polar curves. So we remember that x is equal to r cosine theta, and y is equal to r sine of theta. And so then we just need to find dy d theta over dx d theta, right? Our slope of our tangent line is dy dx, which should be dy d theta. So 2 theta squared times derivative of cosine, so negative sine, plus the derivative of 2 theta squared, which is 4 theta, times your cosine theta, all over, and then the derivative of your y, so 2 theta squared times the derivative of your sine, and then plus your derivative of 2 theta squared times sine, and then we'll evaluate that all at pi. And might be nice to simplify a little bit. First, we can get rid of 2's and thetas from all of this. So really, we've got theta, we got negative theta sine theta plus 2 cosine theta over theta cosine theta plus 2 sine theta. And if we're going to evaluate that at pi, the sine of pi is 0, right? So that's gone and that's gone. So really, we've just got 2 times the cosine of pi, and cosine of pi is -1, so we got -2, and then the pi times the cosine of pi, and again, cosine of pi is -1, so that's just negative pi, so we end up with 2 over pi. Everybody good with that? Or if those of you that are in BC that should be good with that, good with that? So just to sort of give you a little bit of a taste of what the multiple choice questions sort of look like. Let's look at this one. You guys want me to like just let you do one on your own, or you just having me going through them like this is good enough, or do you guys want to do it on your own and see what you get, or? Kevin, Megan. No preference. Megan, you want to just do this one, or should I just go through it? I'll just go through it, unless you desperately want me to let you do it. All right, we'll just go through it. Megan didn't answer. Oh, no, Megan. Okay, all right, perfect. We'll just go through it. So what's the first step in this one? First off, since it's a rational function, we look at it and we say, all right, is there a nice, easy U substitution? The answer is no, not really, because if U is x minus 2, then du is just dx, and that's not going to be helpful at all. But the degree of the numerator is more than or equal to the degree of the denominator. So we will divide. In this case, since this is just x minus 2, if you want to use synthetic division, you can. And I personally prefer that just because it's quicker and easier. Bring down the 6, multiply by the 2, add, multiply, add. Right? And so we'd end up with, what do we end up with here? We'd end up with 6. Oh, sorry, -9. Yes, thank you. We'd end up with 6x plus 8 minus 9 over x minus 2 as our integral now. And then we just integrate. So 6x should become 3x squared. And then the 8 just becomes an 8x. And then this just becomes minus 9 natural log absolute value x minus 2 plus your constant. Pretty straightforward, hopefully. Okay. Now, here's one I'll let you guys take a second to think about. So I'm going to give you a series, sum from n equals 1 to infinity of 1 over the natural log of n plus 1. And it says, which of the following statements about the convergence of this series is true? And they're all converges or diverges by comparison. So I'm going to say converges, and then the arrow is just going to, for a second here, indicate by comparison with, right? So converges 1 over n, converges because of 1 over n squared, or the other options are diverges because of that. So why don't you both take a second and see if you can decide whether that converges or diverges, and by which one you would need to be comparing it to in order to do that. Any thoughts there? Yes. Kevin, you got it. Megan, any thoughts on that, or? All right, so first off, we're just given these two series, right? 1 over n and 1 over n squared. So we got to think about what's going on with the series 1 over n and the series 1 over n squared. First off, we know that 1 over n diverges, right? And we know that 1 over n squared converges, right? And so if we're going to do direct comparison, then that's going to tell us that if 1 over n squared converges, then for this to converge by direct comparison with 1 over n squared, then 1 over ln of n plus 1 needs to always be smaller than 1 over n squared. And for this to make sense, we would need 1 over ln of n plus 1 to always be larger than 1 over n. Does that make sense? Okay, good. So if we think about these series, then if we're plugging in values of n, let's say we plug in, n equals 2. This is a half, and this is 1 over the natural log of 3. Well, the natural log of 3 is definitely less than 2, right? And so if this thing down here is smaller in the denominator than the term in the denominator of this, that's going to give me a larger value. So this, even once we get up to just a simple value of n equals 2, which is giving us 3 and 1/2, or natural log of 3 and a 2 down here, these values are already getting larger overall than these values are. And the larger values of n that we plug in, that's just going to continue. Whereas down here, we need this to be smaller than 1 over n squared. And that is not always going to be true, because this thing down here is going to become the denominator itself is going to become smaller than 1 over n squared. The denominator here, because that denominator gets large much more quickly, in fact, than even the 1 over n does. And so therefore, this is the thing that is true. 1 over ln of n plus 1 is larger than 1 over n. And so therefore it diverges by that, because 1 over n diverges. Does that make sense? I know that's what you said, Kevin. Megan, does that make sense? Cool. That's just kind of sort of the thing. Some of the things you gotta think through. And so we can, just by knowing whether 1 over n diverges and 1 over n squared converges, we can immediately eliminate 2 of the 4 answer choices. And so even if you weren't sure at that point, you've got a pretty good chance of guessing. Let's see here. How about, let's look at this. This is a fun looking one here. We've got r equals 1 minus cosine theta, and we've got r equals 1 plus cosine theta. And they've sketched a graph for us here, which should look like this. And try and sketch my graph correctly here. That's not so great looking, but they've shaded in these regions right here. And then they've given a bunch of expressions for the total area of that shaded region right there. So the options that they've given you are an integral from 0 to pi of 1 plus cosine theta squared d theta. They've given you an integral from pi over 2 to pi of 1 plus cosine theta squared d theta. They've given you 2 times an integral from 0 to pi over 2 of 1 minus cosine theta squared d theta. And they've given you an even more annoying one for me to write out here, 0 to pi over 2 of 1 minus cosine theta squared plus 1 plus cosine theta squared d theta. And so I'll give you guys a second or two. It's probably the last one we do, because I gotta drop my kids off at my parents' house so they can take them to baseball and tennis lessons, so that I can go to school and run the clock for basketball. So this is the last one we got time for here. But why don't you guys take a second and think through it and see if you can come up with an answer that you're happy with. So first off, let's think about what if we tried to do this first one, 1 plus cosine theta squared. From 0 to pi, well, starting at 0, that's right here on 1 plus cosine theta, right? 1 plus cosine theta is the one I drew in blue. So that's going to be starting me there and going towards pi. That's definitely not going to be just this region, right? Because it's giving me all of this other junk too. So we can immediately eliminate this one. Okay. The next one is pi over 2 to pi of 1 plus cosine theta squared. Well, if we think about that one, pi over 2 on 1 plus cosine theta should be starting us right here, right? And then going to pi should be bringing us down to here. So that should be half of this little piece up here, right? But remember that our integral is 1/2 r squared d theta. And so we don't have the 1/2. That means we've multiplied it by 2, right? Which would give us the area of, the whole thing up here, because both of these are going to be identical just because of the nature of those functions. But this is only giving us half of the region. It's only giving us the top part, not the bottom part too. So we can eliminate that one. If we go down to the next one, 0 to pi over 2 of 1 minus cosine theta, well, if we plug in 0 to 1 minus cosine theta, that's going to start us, up here at 1. And then if we go to pi over 2, that's going to bring us down here to the origin, or to the pole. So that's going to give us the right half here to the right of the y-axis with the red. And since it's 1/2 r squared that it should have been, but they've multiplied it by 4, that ought to give us 1, 2, 3, 4 of those same regions. So it ought to be this one. And then that last one is just sort of absurd. That one's, they're trying to I don't even know what they think they're doing there. So that one's just absurd. Yeah. Does that make sense or no? Is that what you guys would have thought it was? Did you guys think, did I start talking about it too soon? All right. We are going to have to stop there so that I can shuttle my children around for their assorted activities before I go to school and work till 9 o'clock tonight.